Okay, so I introduce you Richard Montgomery. He's from UC Santa Cruz, and he's been there since 1990. Retired in 2020, but he's still, I think, as active as ever. I didn't notice any reduction of his teaching. So he had his PhD in UC Berkeley with Jerry Marsden in geometric mechanics. And since then, he has about 70 papers, 2 books, 1 monograph. Probably his most famous papers in like 2000, year 2000, with Ancient Scenario. Annals, it was about new solution of a 3-body problem. I presume you will talk about it now a little bit. No? All right. You look it up. And what else? So we have 1 book on sub-Riemannian geometry. It's about 2002. CIMAT is very much related because he wrote it when he was in sabbatical here about 5 years before that. And then there is a new book just came out this year or last year on the 3-body problem. So it covers about like 2 of his most important contributions. And okay, I think I covered most of it. I let Richard talk about himself for the rest of the hour.
Okay. Muchas gracias por la invitación y la hospitalidad por muchos años. So this is the title, Gauge Theory from Falling Cats to the 3-body problem. And let's see if this thing works. I'll skip the abstract. So over and over again, we'll have a principal bundle. So there's a space on which a group acts. And the quotient space is S. And this will happen over and over again in the talk. So here's a little cartoon. So you want to imagine little groups sprouting out of space-time, huh? These little, lots of G's at each point in space-time. That's how the physicists think about it. And why does it keep going forward? Here's some physicists. Theodore Kaluza, Oscar Klein. People talk about the Kaluza-Klein picture in physics, and that's going to come up in the talk. And then Yang Mills, I think it was the late 50s, they wrote down their famous Yang-Mills equation, which is a kind of generalization of electromagnetism. And then we have this famous person, Gil Ford, did his thesis on the Yang-Mills equations. It wasn't known at the time that they were non-self-dual solutions with finite energy over S4. So he did that with another, simultaneously another group was doing it. Gil and I were both in Berkeley. I was there a little earlier than him, and I was witnessed this revolution in 4 manifolds. It completely changed the subject. And when things are really, really exciting around you, you want to go to all the talks. So that's how I learned gauge theory. There were lots of seminars. I won't bother you with the method, it's there. What Donaldson did, Donaldson got the Fields Medal for this. And here's some people. This guy here, Taus, was a professor at Berkeley, so I remember well taking classes with him, and I know him still. Singer was a professor. I can tell little stories. I wanted to do mathematical physics. There were 4 people to do it with. Singer was my first choice. I made appointments to meet him. 3 times I made appointments. He never showed up. So I had to move on. So Donaldson got the Fields Medal. There's the Atiyah Singer Index theorem. De Hooft wrote down a kind of the first non-trivial solution to these Yang-Mills equations in a sense. Karen Uhlenbeck worked on compactness. So these are kind of the early heroes of the subject. And I learned this as a graduate student. I did a thesis with Marsden around something related, closely related. And then when I went to MIT, I started working on this problem of how a cat lands on its feet. And what happened is this person down here at the bottom, Jair Coiler, who's in Brazil. We were friends and he visited me and he said I should read this paper by Wilczek and his student Shapir. And it explains how to think about how microorganisms swim in terms of gauge theory. And I'll read you the first sentence. The problem of swimming at low Reynolds number is formulated in terms of a gauge field on the space of shapes. Okay, so my task for the next few minutes is to try to explain some of that. Okay, Gil's seen me do this before. Everybody stand up. There's something silly point and freeze it. Now move it around. What does it mean for it to be in the same shape? You're not changing the shape, okay? But you've moved it in space. So we're going to talk about mathematically what is a shape, okay? So that's it. We're done with the physical exercise. Okay, so if you look at this falling cat, this is one of the earliest stroboscopic videos. Of course, I took it off of Wiki. The final and initial shape is pretty close to the same, except for the tail. The tail turns out not to matter much. So whatever shape is, the final initial one are about the same. Well, I didn't say what a shape is. A shape is equivalence class. Two objects have the same shape if you can get from one to other by a rigid motion, a rotation, or a translation. Then they have the same shape. So the cat is moving, changing its shape. This is the shape space of the cat. It's the quotient space of some total space that somehow describes the cat moving by a group action. What is the group action? It's a group, for the cat, it's just a group of rotations. You don't have to worry about translations because the cat's in free fall. The center of mass is just going to do what it's going to do. But the cat wants to rotate by 180 degrees. So somehow, by choosing a loop in shape space, you get a change in the orientation of the cat. So again, we have this unifying theme. You have a group of rigid motions, configuration space of the cat. I will describe more what I mean by that. And then the shape space. So that's the central object that comes up again and again. So the utility of this picture for understanding the strategies of falling cat for righting herself or for swimming a microorganism to swim is that a reorientation strategy, or for a swimming macroorganism, a translation strategy, is a loop in its shape space. So we actually do that walking, huh? You're making a loop in your shape space when you walk. Okay. How does a loop in shape space lift? So I have ignored that point. I draw a loop downstairs in this S. How do you lift it? So here's a little picture. This is a standard picture for gauge theory or connections on a principal bundle. This is the tangent space to shape space, and the little arrow represents an infinitesimal deformation of the shape. And this gadget called a connection, which is a plane that's orthogonal to the fiber. The group 5, this fiber represents all rotates of the fixed shape. So there's a plane that's perpendicular to the group motion. And that plane is called the horizontal space. And this process of taking the little vector here and lifting it is called horizontal lift. So that's kind of the basic structure of principal bundles with connections. Now I threw a connection on it. So let's see if I can read it here. Paths perpendicular to the group orbits. Horizontal paths, the little thing covered up there, horizontal paths are paths perpendicular to the group orbits. The group orbits are called the vertical space. So if you move in the group's direction, that's vertical. Perpendicular group is horizontal. And what I want to now show you to connect this with the falling cat is that horizontal motions are exactly motions where the total angular momentum is 0. So I kept saying perpendicular. So to have a perpendicular, I need a metric. And I need to tell you what this space Q that somehow is describing the cat is. So I'm going to drag you through 2-3 pages of algebra now, which is kind of a no-no in giving a big talk like this, but I'm going to do it. Okay, so we're going to model the cat as a collection of n points in R3. So you can kind of think of them, the head, the tail, maybe the paws, the hips. So you put a bunch of points, connect them by maybe massless rods, and that's going to be the model. Now, I'm lucky, that's exactly the same model for the n-body problem. This is exactly how you describe the n-body problem, n points in R3. So I said, think of them as marker points. They have masses, ma, and we're going to define an inner product, which is the natural one that comes up in physics. It's called the kinetic energy. So 1/2 mass times velocity squared. That's a formula for kinetic energy. And that's a quadratic form in the velocity. So VA is the velocity of the 8th marker point when you're having this model for the cap. So there's a kinetic energy. And you can barely see on the bottom. This is one slide I should have lifted that up. That little formula is a formula for the inner product, the mass inner product. So now what I have to do, in the next 2 slides, I have to tell you what vertical means, and I have to work out what's perpendicular to vertical. And we're going to see by hand that it means angular momentum is 0. So to work out horizontal, what does it mean to be horizontal? So here's how the group acts. It just rotates all, right? It rotates all the points of your finger. That's how the group acts. It just rotates. What's an infinitesimal rotation? If you just barely rotate, it's the same as doing cross product by some omega. And in physics, that's called the angular velocity. It's the same omega for each marker. The same omega for each of the n bodies. So the vertical space looks like omega cross q, or omega cross q in quotes. It just means omega crosses with each marker, each of those n markers in R3. So now here's the algebra. Suppose V is perpendicular to all these velocity, all these vertical vectors. Then if you unwind the definitions, it means MAVA dot omega cross QA is 0. You use an identity with the triple product. You slide the omega there. You slide the omega out here. And you've got omega dot, the quantity that's called the angular momentum. That has to be 0 for any omega, any infinitesimal rotation. The only way that happens is if the angular momentum is 0. So horizontal is the same as angular momentum is 0. And that's what connects this geometric perspective to physics. Because when you let go of the cat, it has no angular momentum. We're not going to throw the cat across the room. Very gentle. Over the couch. Okay. All right. So proposition, I just said it, a deformation or motion of a located shape, a point up in that Q, is mass metric perpendicular to the group orbits if and only if its total angular momentum is 0. That connects the geometry to the physics. And it works exactly like I just said it for the n-body problem. So the gauge field, those earlier physicists, what Wilczek called the gauge field, is really the angular momentum. So angular momentum 0. The horizontal paths are given by some connection equals 0. I wanted for there's people in here who do Riemannian geometry for a living, so I wanted to say the same thing in Riemannian geometric terms. This is pretty close to this statement that if I have something called a Riemannian submersion in a geodesic that's perpendicular to a fiber at one point is perpendicular at every point. So that's a kind of conservation law in Riemannian geometry. So there's a picture again. This change of the cat starts upside down and wants to come right side up. This is called the holonomy. So this is just language. The total space is the configuration space. The connection is given by physics, it's zeroing the momentum. The group G is called the structure group. That's shape space. You have a loop in shape space that represents the cat's attempt to reorient. Just a little aside, Taubes and Gill and most people in gauge theory, the connection was a dependent variable in the PDE you're solving for. That's not what I'm doing here. I've got a fixed connection. It's the angular momentum 0. So it's a different perspective than the beginning of the talk. So here's some questions. What's the optimal reorientation strategy? What's the best change of shape to have the cat flip up? What's the best one? In the principal bundle language, what's the shortest loop with a given holonomy? And then a few years before I was here, well, 8, I realized it's the same as a question in a field called sub-Riemannian geometry. And the problem is to find a geodesic and a sub-Riemannian metric that connects 2 points. So those are all the same problem. So again, back to this picture, and I'm just going to try to tell you on the picture what the sub-Riemannian metric is here. So I have my group acting on my total space, my space that represents the cat, the located cats. It's acting isometrically on Q. So the quotient inherits a metric. And what I can do is I can take that metric and I can restrict it to the horizontal space. Because the cat can't move. Once it's falling with zero angular momentum, it can't all of a sudden decide, I want to rotate and have non-zero. I can't do that. So you're stuck moving in these planes. So now you want to connect a point here to another point here, but you're only allowed to travel on these horizontal planes. And then you can ask for the shortest one. You have a way of measuring distance here. That's sub-Riemannian geometry. Oh, right, yeah, I wanted to do that. I'm not sure, well, we'll do it anyways. It's always good to have at least one example. Now, when you're taking a class, in a physics class, the example is always R4 across the group. It's always what we call a trivial bundle. But as mathematicians, you want to have one non-trivial example. And the one that comes up over and over again, which is my favorite, is the Hopf vibration. So this S3 sits inside C2, 2 copies of the complex numbers. And the unit complex numbers act. And the quotient space is a 2-sphere. And here's the picture that you can find all over the web. What is this a picture of? This is called the Hopf vibration. The whole thing is supposed to be R3. I'm sitting in R3. And I remember very distinctly, we had a guy named Jeff Mess as a grad student. And I couldn't understand why everybody was drawing pictures in R3 and telling me that it's S3. And Jeff told me, what's wrong with you? You live in S3. And I was like, what are you talking about? So you've probably all seen how you can take a plane and use stereographic projection and turn it into a sphere. R3 is a 1-point compactification of S3. So you can think of the space we live in as a 3-sphere. You're going any direction and you get to infinity. Go any direction, just keep going forever and you get to infinity, and that's S3. So these tori are called Clifford tori. They're the inverse image of meridians on the sphere S2. The circles that go around are the Hopf circles. So they're the group orbits. So it's just good to have a picture, some picture of a non-trivial bundle. Try to prove it's non-trivial. Figure out what the connection is. There's metrics lying around. It connects with contact geometry. So I said, talk sponsored by CIMAT and the Hopf version. Okay, so I did write 2 books. This book I wrote while I was here, 1997 to 8. I wrote 90% of it, and then I thought it's really hard to go from that last 90% to publishing. I actually hired an editor who was an ex-mathematician. So thank you, CIMAT, for the support while I was writing that book. And then during the pandemic, I was inspired to write another book, and it got published this year by Cambridge. And I think the publication date was December 2024. Okay, we're going to switch. Are we going to switch fields? No, I promised 2 theorems. I did promise that in the abstract. So I'm going to give you 2 theorems. All right. Yeah, that has a good picture, but all right, this is just copied right on my blog. So let's read it and then go back to the picture to make sense of all the words. Okay, suppose you have one of these, instead of S, I wrote M here. So you have a principal G bundle, Riemannian metric. Okay, it has a special type, constant bivariant type, little asterisk. I'll tell you what that means. Let H be the induced connection. In other words, those planes I kept drawing pictures of. Let XR be the Riemannian exponential. So Riemannian geodesics are written this way. Gamma sub R of t is X bar TV. The B is the initial velocity. That any horizontal lift. So here's the picture. Let's do the picture instead of the words. Okay, here's your Riemannian geodesic. Projected to shape space, horizontally lifted. Those are your geodesics in sub-Riemannian geometry. Once again, take a geodesic for the Hopf vibration, for example. Projected to S2, horizontally lifted. There's a sub-Riemannian structure on S3. Those are the horizontal, those are the geodesics. So that's that picture, that theorem that I'm kind of proud of. Okay, there's one more thing underlined. Normal sub-Riemannian geodesic. I'll get into that later. So there's these 2 asterisks to describe. So there's a formula. This is a formula for the sub-Riemannian geodesic is expressed in terms of the Riemannian one and the groups acting on the space. So you can look at the picture to understand the formula. You see, here's the Riemannian one, and you go backwards in the group direction by this amount. So that's at, here I'm going from the sub-Riemannian up. If I go backwards, I go from the Riemannian one down to the sub-Riemannian one. So that's the picture of what that theorem says. And it's been very useful for me. I used it for the falling cat stuff, for answering those questions. So that's the theorem from my first book. I do want to fill in the asterisks. This metric on the big space Q, if you restrict it to each group G, you get a metric on G. I want those metrics to all be the same. And there's something called a bi-invariant metric that's given by Killingform, if you know what that is. I want them all to be of the same multiple of the Killingform. That's what constant bi-invariant means. Okay, what about normal versus abnormal? The reason that I'm known in sub-Riemannian geometry and that the control theorists talk to me is that I have a, what's a good way to say it? There was false theorems in the literature that said in sub-Riemannian geodesics, every geodesic satisfied something that the geodesic equations, which I don't want to tell you what they are, but that theorem talked about them. And I found ones that don't, that people have missed. And it has to do with singularities in path space. So I found these strange other geodesics that in some instances you can't get rid of. That's basically the reason I wrote that book, because of that theorem. They're difficult to understand. Their existence reopened a basic question. Are all Riemannian geodesics smooth? So that I asked that in 89. Other people have thought about it. It was solved in January of 2025. The answer is no. Not all Riemannian minimizing geodesics are smooth. Okay, I know all these people except Sacelli, Sigalotti, and Socianovo. I think he's the graduate student. All the other guys said, yeah, he's going to do all the work. You ask him questions, they talk to him. And the example is really simple. The proofs are hard. Examples on R3. It's a fun paper to look at. It's well written. Anyways, it's wonderful to have a question that you asked a long time ago, 35 years ago, answered. So I'm very happy about that. Okay, next half of the talk. I'm about halfway through. Good time for questions. Any questions? Ezekiel, ¿tienes preguntas? Okay.
No, por ahora no, gracias. Estoy escuchando.
Okay, you want to go on to that second half, or you want to ask a question? Something, Jax? Okay, this is from the cover of my book. If you look at the cover of my book, that's an artist took that picture and did something to it. Here's a solution to the three-body problem. It's called a break orbit. If you look at where the bodies go, eventually, ooh, they all stop. And then they just reverse their path. That's a periodic break orbit. About 300 of those are known now. No, there's in the thousands now. And there's a whole little industry of people that work on these things. A guy named Christoph sent me this GIF. Okay, so that's this particular solution. Let me tell you how the problem fits in. So before Newton, Galileo said the laws of physics are invariant under my group. He didn't exactly say it that way. And he said, my group contains your group. Because our group's a group of rigid motions, huh? Right? And Newton listened to Galileo, and then he said the laws of physics can be written as a differential equation, which are invariant under Galileo's group. And here they are. He doubled out his group. His grad U. The grad is the grad with respect to that inner product, that mass metric inner product. I think that's on the next slide. And the U comes from the gravitational potential. It's the negative of the gravitational potential. The reason I put a negative in, a gravitational potential is always negative. And I like to think of symbols as positive. So it's kind of traditional in my area of celestial mechanics to write things this way. So there's the n-body equations. And there's the definition of grad, right? You use this funny mass inner product. There it is again. So du q of v, that's a one form. There's a vector. The whole thing's a scalar. You write it as grad u inner product v. That's the n-body problem. I'm going to do it in the plane. My bodies are going to move in the plane. They're not going to move in space. So I'm going to think of the plane as n copies of C. So each R2, right? Instead of x comma y, it's x plus iy. So I think of the plane R2 as C. And the group is translations and rotations. I should really put a little funny thing here. It's a semi-direct product, but it's a space, it's translate or rotate. And Newton's n-body equations descends to a family of second-order ODEs on shape space. The family is parameterized by the angular momentum. In the case angular momentum equals 0 is by far simplest because it looks exactly the same. When the angular momentum is 0 on shape space, it looks like this. Del s dot equals grad u of s. The u is invariant under, oh, the RABs here are the distances between the bodies. If you rotate everything rigidly or translate, those distances don't change. So the U is invariant under the group, so it descends to the shape space. There's a funny del here because this thing inherited a metric from Q. But it's no longer flat. The shape space isn't flat. And you can compute that shape space is something that is called the cone over Cpn minus 2. This is computation. So there's a complex projective space is a thing that some of you know about. There's pictures in my book. You can see pictures in my book. And maybe a better way to think of it, it's the space of oriented, I should have crossed that word out. Oh no, that's right. Oriented congruence classes of planar n-gons. So it's like planar n-gons a la Euclid, except you're not allowed reflections. This thing here, the Cpn minus 2, is oriented similarity classes. You don't care about the scale. That's what the Cpn minus 2 is. You're not caring about the scale. So that's what shape space is for the planar and body problem. And I want to tell you about the cone point. I'm sorry, I have something wrong with my voice. I want to tell you about the cone point. So maybe people don't know about cones. Whenever I have a space like Yellow's pack, I can take the cone over it. I can put a point here and I can connect it by rays. You can take the cone over any space at all. You get a new space and it has a singularity. It's called the cone point. The cone point is total collision. That's the point where things get really difficult. And here is a total collision orbit that Lagrange found. You can start any masses off on the vertices of an equilateral triangle and you drop them. You let them go from rest. They stay equilateral and they shrink to a point. And after that, you're done. Bang, you can't keep going, okay? Because it's, after velocity had gone to infinity, things broke down. So that's a solution Lagrange found in 1772. It represents a cone point for 3 bodies. And a theorem, I think it's by Shazi, the only road to total collision, or the only roads to total collision are through these things called central configurations. What's a central configuration? It's a configuration, so endpoint masses, so that when you let them go from rest, they do that same thing. They just shrink and they keep the same shape and they go to total collision. So that's the only way in to total collision is asymptotic to one of those. So the initial velocity of 0 involves by shrinking to the center of mass. So that's a definition of a CC, central configuration. Here's some pictures that my collaborator Rick Moeckel made. Come on, go. Okay, so this one, the one on the right, the 4th body's in the middle. And this one, they all look like, okay. And Rick just unwinds the movie. I mean, I would prefer a big bang there, but I didn't want to redo his movie. So the simplest total collision TC, total collision solutions are these. The ones generated by central configurations, but that's not all of them. There's lots more. But all of them converge asymptotically to one of these. So let's say what that theorem is. Let's see. I'm going to jump forward to that. Yeah, I better go back. Okay, I better follow my slides. I have to go run through it again. You can decide to imagine what you think that is. That picture. Okay, let's go. All right. You can think of central configurations as critical points. So there's a reformulation. The U was a function on shape space, but you can make it homogeneous of degree 0, scale invariant, by multiplying it by the size of the body. That's the size relative to the mass metric. Now you have a function that's only depends on the similarity classes of the triangle. So it's a function on the CPN minus 2, and it's a theorem. Configuration is a central configuration if and only if its similarity class is a critical point of this tilde U. So that's a theorem. It's probably 100 years old. I mean, Euler and Lagrange do this for n equals 3. And then probably in the 1880s, sometimes people figured it works for any n. So we're going to call a central configuration non-degenerate if the critical point is non-degenerate, and we're going to say it's isolated if the critical point's isolated. Open question number 1 in my book, and it's an open question in these problems of Smale that he wrote in 2000. Are the central configurations always isolated? So that's an big open problem. It's solved for 3 and 4. It's solved for 5, almost. So you can look in the book for details of what's known. Everybody thinks the answer is yes, but it's a hard problem. You can phrase it as a problem in real algebraic geometry. Okay, regardless of all that, the only road into total collision are along central configuration. So what do I mean by that? This is a theorem of Shazi and Sunman. Suppose a solution suffers a total collision. So you know it ended up with everything crunched to a point. All the n bodies collided. Then you can rescale it, just divide by the size of the body. And now you're sitting on a unit sphere in this Q. The Q is just a Euclidean space. You're in the unit sphere. And you can look at what happens to those points on the unit sphere. So the theorem is that the set of accumulation points of those things is a closed connected subset of the set of normalized central configurations. So I state it in a very careful way because we don't know if there's a continuum of these central configurations. So here again, this is the sphere. It's the normalized centered configurations. I kind of hid this from you. I made the center of mass 0. So it's standard physics trick. That should be a 1 there, not a Q. It should be a 1. This is the hot vibration. The map from S to the C, that should be a 2, to the CPN minus 2. That's the hot vibration when n is 3. If I do this for n equals 3, this is S3 and this is CP1, which is the same as S2. This is the hot vibration. Take you from a normalized n-gon to its oriented similarity class. That's the hot vibration again. And here's a picture of an isolated central configuration on the sphere. There's going to be a whole circle of them because the inverse image of this projection, like with the hot vibration, the inverse image of a point is a circle. Okay, so this is the theorem I decided to present. I don't know, I'm a mathematician. I feel like I gotta give you a theorem. I can't just I'm like obligated to give theorems. This is the theorem that RM and Rn proved in 2024. Suppose we're in the planar n-body case, and suppose for a given mass distribution, the central configurations are isolated. So they can be degenerate, they just have to be isolated. So we're saying no continua. We're saying the answer to that open question is yes. We're assuming, and we know it's yes for a lot of masses. So that means the set of central configurations, remember we normalized, we have this S of t, it's a curve on the sphere. It's got to be converging to one of a finite number of circles. But what it could do is it converge, it could spin around and around and around. That's called infinite spin. And we knew, he and I together, pretty much everybody working in mathematical celestial mechanics, we knew that was an open problem with there's a false proof in the literature. Anyways, so it's one of these things again. We're like, oh yeah, that's proven. You look at the proof, and you go, you didn't prove anything. Anyways, so we have a whole appendix why it wasn't proved. But we prove it, okay? If the central configuration is isolated, boom, it can't spin forever. Okay, since it uses ideas from gauge, I'm gonna drag you through the proof, and we'll be done. Okay, oh my God, this is a Rick Moeckel slide. Right, so it's just said a bit differently by the other RM. As a total collision solution approaches collision, it's conceivable that it spins or spirals, so the shape converges to a circle of CCs rather than to a specific point on that circle. For non-degenerate central configurations, Shazi, he's 1920s, 1930s, showed it doesn't happen. Infinite spin is impossible. Our main result is to extend this to degenerate CCs, provided they are isolated. So that's the theorem. If a total collision solution has if its shape converges to an isolated CC, you don't need all of them to be isolated on the whole CPN-2. You just know you're going to an isolated one. Then the angular value converges. In other words, you're actually on the sphere, you're converging to a point. All right, I'm going to skip the bottom part. All right, so like this falling cat, and I can't get away from it. So this was why it was hard to do, because I understood about falling cats well enough to see that it wasn't all, why there was a hole in this old argument. So what did Rick write? We know, Shazi knew, people knew many years ago, if you go to total collision, the angular momentum has to be zero. That was a theorem from 100 years ago. So how is it possible for a cat to drop a zero angular momentum? Okay, so this is Rick's slide. So I already did this, huh? The point is that the falling cat could do a reorientation where it spins forever. It just keeps spinning on the way down, even though its shape is frozen. Seems pretty weird, doesn't it? But it's possible. So I want to show you that it's possible, and then show you that it doesn't happen in our case. All right, okay, so this is an example with three bodies. So again, we've got these 3 point masses, the planes are on momentum. So what I've done is I went from the falling cat to the 3-body problem just by replacing the falling cat by 3 points, huh? A triangle. So Rick said, I'm going to imagine 3 people on a slippery surface of the 3 ice skaters. I don't want them joined by imaginary sticks. You're all connected by rubber bands, huh? Okay? And you're pushing and pulling on each other. You can change your shape, huh? But you always have zero angular momentum because you can't push off. It's super slippery, huh? It's oil. Maybe that's a better way to think of it. Super slidey oil. So you have a curve in the shape space of the triangles, which is a sphere. It's this hop sphere, the S2. And here's the corresponding zero angular momentum curve. Okay, so that's for that one. Because you can write down the connection form, you can write down the horizontal length, you can see what happens. So this particular one settles down, finite amount of rotation. But this one doesn't. Let's have it go for a while. So what's the difference? There's the curve in shape space. It's converging to the equilateral triangle, but it just keeps rotating. The difference, well, I think we wrote it down. Does anybody want to make a guess what the difference between the 2 curves is? This spiral? Well, it would have been nice if he...
You only make the left.
Well, he should have had it converging to a point. I'm sorry, I didn't fix that. See how this one converges to a point there? This one here, this should have been a point. This should have been converging to a point here. Okay? So that makes the question a little bit hard to ask. He does it here. Again, this one should be converging to a point. I'm sorry, Rick, that I didn't fix your slide. That should be spiraling into a point. The difference between these two spirals, this one has finite length, that one has infinite length. That's what you need. You need finite length. For planar and body problems, possible introduce local shape. So this is just about, this is how you reconstruct the angle. And the theorem, that's pretty easy to prove. If the shaped curve has finite arc length, then you converge up in the sphere. So you need finite arc length. So how are we going to get finite arc? So now we're almost at the end where it gets technical. How do we get finite arc length? So if it's converging in, the convergence is exponential, and the arc length is finite. That follows easily if it's a non-degenerate rest point. In other words, like in Morse theory, that if you take the derivative of the second derivative of the critical point, the Hessian at the critical point, if it's an invertible matrix, you can show by hand that the arc length is finite. For degenerate ones, it's harder. And the dynamics on the center manifold is well approximated by a gradient flow. There's a center manifold in dynamics when there's all kinds of stuff I'm hiding here. What's hiding is there's a way to blow up total collisions and get dynamics on you blow up the total collision and turn it into another sphere, and you get dynamics there. So I'm hiding a lot. But at the end of the day, there's a dynamics on the center manifold. And it looks almost like a gradient flow. And then because of my old days in gauge theory, I knew some analysts that told me, oh, this is very important. There's something called the Leibniz gradient inequality. If there's algebraic geometers in the audience, they've heard of it. And it's an inequality that lets you prove that the arc length is finite. But you have to use the dynamics on the base, because we can write down counterexamples of things where you do spiral forever. So there's the Leibniz gradient inequality. If you have a gradient flow where the F is analytic, then any solution which has a limit point has finite arc length, and there's his gradient inequality. Gradient of f of x is greater or equal to norm of f of x minus f of x naught to a power alpha, and it's important that alpha is less than 1. So you can read about that in the paper. So that's the last theorem. I think and that's it. Oh, yeah. Okay. Questions? I'll get 10 minutes for questions. Ask about anything. Yeah.
I'm confused about something. No? So you have this the configuration space of shapes, no, in the three-body problem.
Configuration space. So I think of them as located triangles. Triangles actually, and then you have the shape space.
So you have this is a cone of CPn minus 2.
Right.
And I understand that the vertex, which is the only singularity there, is when everything collides.
Right.
What happens with the configuration where you have a subgroup of points that collide? Shouldn't that be also singularities on the thing?
Okay. So this is the picture for 3. Okay. So I'm gonna answer your question for 3. Okay. So if you have 3 bodies colliding, then this cone over CP1. CP1 turns out to be a sphere, and the cone over a sphere is just R3 when you use spherical coordinates. So I can draw a shape space here. This is total collision, that's the cone point. And what happens, it doesn't look bad, but if you look at the induced metric, it blows up there. These are binary collisions. So these 3 rays coming out means either 2 of them collided and one's far away, right? There's 3 ways it happens, yeah? So these are the ones you were talking about, right? Isn't that what you
Yes,
were talking
yes.
about? And those, as far as the metric and connection are concerned, those are fine, but for the ODE, for Newton's equations, those are bad points because forces go to infinity. So you have to do a lot of work around these points. And just so you see it here, these are the central configurations of Lagrange. So there's the equilateral triangles, the top and the bottom of kind of the north and south sphere, those are equilateral. And 5 years before Lagrange, Euler found collinear central configurations. So 3 of them in a line, and one of the space observatories is up at one of those points. That wasn't what you
So
asked.
if I understand correctly, those collisions are going to be observed in the connection, not necessarily.
Yeah, they're not a problem for the connection. The connection can go right through them. But the triple collision is a problem for the connection. But
The double binary collisions, how do I understand them? How do I understand the double collisions? If I see,
how do I understand them?
I still don't, there is something I'm
I
missing.
understand them with a lot of work. All right, I'll tell you how to think about it. See if I have another picture of Rick here. He has another really good picture. I get most of my pictures from Gil or from Rick, because they're very good at that. There it is, we got it. The other picture. Okay, so here's another picture to try to explain your question. So here are there's total collision, those same 3 rays. Okay, now I fix the energy, and the energy is negative. Okay, so when you have negative energy, that's the only time you can have bound orbits. And what happens if I have negative, suppose I have a solution where the third guy's flying out to infinity, and these 2 guys are in like almost like the Earth and Moon, huh? What that would look like here is a little orbit just going around here, huh? It'd just kind of be spiraling out like that. So, yeah, does that help a little bit? Little bit. So when you go way out here, it almost looks like the 2-body problem, which is a solvable problem. In this area, it's quite complicated, but out here, it's almost 2-body, which is almost Kepler. Yeah.
Maybe I try to. I think what he's saying, see if it's true and if you accept it, is that okay, when you let's say with three bodies, so if you go to the shape space, just the shape space without the dynamics, just the shape space, the quotient of the configuration space by the rigid motions, and so there's only one singularity, triple collision. When you have double collision in the shape space, there's no singularities. It's just ordinary,
That's exactly right.
Just 3 rays, or if you just quotient even by rescaling, it will be just 3 points on the sphere. But there's going to be problem with the dynamics on the shape space. So you have the space is regular away from triple collision. But the dynamics are going to be a problem. As I say, the forces will go to infinity along these rays, although the space will look perfectly fine along these rays. Now, with more, with a larger number of bodies, so you have many.
Still no singularities except at the cone point.
Exactly. So the only problem is going to be the total collision, right? And the rest, there will be problem with the dynamics. You have to deal with it when you look at the dynamics on the shape space, but at least the space is not singular away from the total collision.
And mathematically, the reason is very simple. There's a theorem that says if you have a free group action, you know what that word means, free? If you have a free group action on a space, the quotient is again a manifold. The action of rotations is free every place except the total collision. Yeah.
But even if there is only double collision,
no
the
problem.
stabilizer is triple.
Right.
¿Hay alguna métrica de manera natural sobre el espacio de n polígonos?
Sí.
¿Qué significa la geometría riemanniana?
The n polygons or the quotient or the shapes of n polygons?
Ajá,
What
el
is the
espacio de clases de congruencia de polígonos.
Sí. SOS es con over CPN minus 2.
¿Y hay alguna métrica riemanniana natural?
Sí, es un métrico Riemannian, excepto por el punto cono.
Whenever
Everything
you
except
have
the
a
cone
quotient
point.
of a space by action by isometries, as in this case, you just take the distance. You can just take the metric on the quotient, just the distance between the orbits. Yeah, so
Yeah.
that's a natural metric that goes to the submersion. Okay.
Por ejemplo, la longitud de una curva con esta métrica es un hecho geométrico, quizá volumen de un tetraedro o algo así.
¿Qué es el? No entiendo el último
Sí,
parte.
la longitud de una curva en este espacio de polígonos tiene un significado geométrico, quizá el volumen.
Sí, geométrico es en línea. It's a straight line in the big space, the big cube. It's a straight line that has zero angular momentum. It's all the end where the polygon is moving. You're trying to connect two polygons. Just draw straight lines between them, but make sure that the total angular momentum, which you compute with the formula with total angular momentum, is zero. That's what the geodesics are.
Okay.
So you can write them down and look at them and play with them. They look weird in the shape coordinates, but you can understand them well by going up to the Euclidean space. Yeah?
Okay.
Do you have some example with phantom frames and how it changed the geometry of the configuration space?
Say it again.
Some example with constraints.
Oh, with constraints. Constraints on the configuration space. Yeah, you could do, I've thought about it on the sphere. You could just say all the points are constrained to a sphere, and I've thought about it a little, but I tend to stick to this framework because it fits the classical Riemannian. Yeah.
Another question. Do you know, for example, a real world example of the n-body problem that is not the K-pervasive?
That is not what?
An example with some weird geometry that is not Kepler. For
What?
example, the solar system is an n-body problem, but it's basically just the two-body problem, no? Do you know some example of a real that is not a simulation?
So some example that doesn't look like kind of a bunch of Kepler problems?
Aha,
You mean mathematically or in the stars?
in the stars.
No, I think people do with three bodies. I don't know a whole lot about it. I have tons of mathematical ones. Well, you saw one you saw a picture.
Yeah.
So we found this famous figure 8, and the astronomer I asked him, people got excited about it, and he threw two bodies at each other and see how often they become figure 8s. And he told me that he estimated the probabilities there's between 1 per galaxy and 1 per universe. So it's not a lot.
Okay.
So far none of them have been found. There's no solutions.
Hola, Richard. I have a question.
And who is this?
Who's this?
Is it Ezekiel?
Ezekiel. Okay.
Yeah.
Thank you for the presentation. I like a lot this result on the non-spin for isolated configuration. So I have two questions. The proof, I imagine that it works similarly for parabolic motions. It's the same proof, probably. Instead of total collision, because you have this duality in.
I haven't thought about that, Ezekiel. I understand your question. Is there an infinite spin problem for parabolic? I guess there must be. Yeah, I think it will work. I think it must work identically, but we haven't thought about that.
Yes.
I'll write Rick and I an email.
Okay.
I haven't thought about it, but I'm almost sure that it will work.
Okay. The new thing is the use of the Lukasiewicz theory for the analyticity of the potential, but I don't see where you use the fact that the central configuration you are approaching is isolated. What is
Yeah,
this?
Rick and I argued about that. He never, at one point, he convinced me that you needed it. And yeah, it's quite subtle. I think it works regardless, but there's a little hole in the proof. I think the whole had to do with estimates over in this patch being the same here, and if you switch to different patches, that bothered me too, and I wanted to take out isolated, but Rick said no, and I trust he's more careful than me. So
Okay.
I trust.
Excellent. Thank you, Richard. Nice to see you. Excellent.
Okay, thank you very much. All right.
Again, this is the CIMAT.
Thanks. Appreciate it. Okay, I made it.
Let's go for some.